Okay, we are talking about reviewing for the first chemistry 6 weeks test. This is third hour, and people are a little more awake, so we'll kind of see how things go here. Main topics we covered. The first big topic we looked at was how science works. I'm not going to spend a lot of time on this slide. Big things to remember is that science is not a single method. It's not trying to get from point A to point Z. You don't always start with a question or a problem. You don't always end with a conclusion. All the parts along the way are very important, but sometimes you go backwards. Sometimes an observation you make will lead you to make a question. Sometimes your research will lead you to change a hypothesis. So it's a continuous, multi-directional cycle instead of just being a straightforward path. I do want to talk about how to write a good hypothesis. Remember, a good hypothesis is a testable if-then prediction. Okay? If I eat nothing but Big Macs, then I will have a heart attack in 3 weeks. Okay? If I water my plants with Mountain Dew, then they will glow. Okay? The if part is something that I am changing. The then part is something that I am waiting to observe or measure or record. And that leads us into talking about independent and dependent variables. The independent variable is the thing that I am changing. That's the if thing. The dependent variable, that's what I am waiting to see something happen to. It depends on my independent. If that makes sense. Independent is the one that I change. Okay, that's why the I in independent is so important. It's the one that I'm manipulating.
So what do you do, flower? What do you not do?
Maybe not do. Because I'm not growing, the flower's growing, right? I'm the one who's choosing to add not do. Okay, good question. Thing that you're measuring or observing. You're waiting to see if something happens. Okay. In a good experiment, you've also got a control group. Your control group is something that you sort of use as a measuring stick to test other stuff against. Okay. So let's say that I want to see if, giving my plants Mountain Dew versus giving my plants root beer, how that will affect their growth. So maybe I've got a group of plants that I give Mountain Dew, another group of plants I give root beer to, but I've got another group of plants that doesn't get anything. Okay? They don't get the variable. So these would be plants that I just water with normal water. Okay, they're not going to get to drink soda and get extreme or caffeinated or whatever. And that's there so that I can compare what would happen if my variable wasn't being changed at all. Okay, that's the only reason you put a control into an experiment. That's not to be confused with constants. Constants would be things that are going to stay the same in every setup. So if I'm growing all these plants, I want to use the same kind of plant. I want to grow them in the same kind and amount of soil. I want to grow them in the same kind of pot. I want to give them the exact same amounts of liquid at the same time of day. I want to make sure they're all getting the same amount of sunlight. The temperature that they are in, the humidity that they're surrounded by is going to be the same. I want to keep everything else as close to identical as possible, so that I know that if there's difference, it's because of the thing I'm testing, not because of some other randomness. Okay? I want to control that experiment as much as possible. We did talk about when you're graphing variables. Does anybody remember the little mnemonic that you use to remember what goes on the x-axis and what goes on the y? Try mix. Very good. Okay? Because your dependent variable you're going to put on the y-axis, okay? Your independent variable, when you're changing, goes on the X. Now, if I'm like measuring the number of heartbeats a bunny has in a given amount of time, okay, which one of those am I actually observing? The time or the number of heartbeats? Yeah. I'm observing the number of heartbeats. That's what I'm counting. So the number of heartbeats would go on my y-axis, and time passing is going to go on my x-axis, even though I'm not controlling time, probably. Okay? But I'm also not measuring it. It's just happening. There were a few questions on your first checkpoint about different kinds of lab equipment. Remember, we had that activity where you pulled out all the different lab equipment and you had to identify what it was for, and you had to draw little pictures of it. There might be some questions like that on this. There might be something like, okay, if I want to precisely measure the volume of a liquid, what apparatus do I use? Graduated cylinder. What if I want to take the volume of a solid and it won't fit in a graduated cylinder? What can I use? Use a Eureka can. Very good. Okay. If I want to take the mass of something, what do I use? Not scale.
Well,
It's a balance, right? Okay. Scales are for weight. Balances are for mass. If I say want to pick up a really hot beaker, what are some different things I can use? I can use beaker tongs. What else? The hot hands. Yeah, the little rubbery thing. Also, if I've got a good pair of thermal resistant gloves, I can just pick it up with that. So there might be a few questions on there about apparatus. Okay, does that make sense? Any questions about that? Okay. There was quite a bit of math stuff during the first couple weeks of school, and so I want to kind of refresh your memory on that. I know it's been a while. We talked briefly about how scientific notation works, dimensional analysis, which you can use for making conversions, and then also various rules regarding everybody's favorite, which is sig figs. Scientific notation, main thing you need to know about that is it is useful for either ridiculously large or ridiculously small numbers, okay? And scientific notation has to be in a specific format. It is always going to be in the format digit, point, digit, times 10 to some kind of exponent. And that exponent, if it is a big number, then it's going to be positive. If it is a small number, then it's going to be negative. And here I'm defining big as anything bigger than 1. I'm defining small as anything smaller than 1. You might have a question asking me about scientific notation. Probably not. I don't feel like that's one of the more important things to cover. Dimensional analysis, remember, is a way that you can do conversions. And the way you always do dimensional analysis is you always start with what you're given. You put it over 1. And then you're going to multiply what you're given by a number of factors until you get to what you want. And it's really easy to know what those different factors are because you look at the units, okay? So if I've got a certain kind of unit that I'm given in the first step, in the very next step, that same unit goes to the bottom. And it turns it into a different unit. So now I've got a new unit. And if I have to make another conversion, that unit on top is going to go to the bottom in the next step until I get to the unit that I want. And then once I've got this all set up, I take everything that's on top and I multiply it together. And I take everything that's on the bottom and I divide by each thing. Okay, so all the numerators multiplied divided by each of the denominators gives me my answer, gives me what I'm trying to convert to. Very simple. I want to talk about the rules for significant figures. Remember, significant figures are a system put in place to help take some of the inaccuracy out of math using measurements. And so it's important to be able to know, first of all, what the rules for those sig figs are. There's 4 rules. Actually, there's 5, but there's only 4 that you really have to be consciously aware of. The first one is if you have a non-zero, is it significant or not? No, it's not? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are totally significant. Yes. Okay. Again, that's anything like 1, 2, 3, all the way up to 9. So if it's not a 0, you can count it as a sig fig. Next rule is if I have a sandwich 0, zero stuck between a couple of non-zeros, is it significant, yes or no? Yes, it totally is. So in other words, if I've got something like 2004, the 2 is significant because it's not a 0, the 4 is significant because it's not a 0, and these 2 in here are significant because they are sandwiched. It does not matter how big the sandwich is. They are significant. What if it was 20.04? They are still significant, so now I made a clown face. Okay, questions? All right. So then what about what are called following zeros? Okay, these are zeros that are to the right of your non-zeros. Are they significant or not? If there's a decimal present, they are. Okay? So, if there's a decimal, then we say they are significant. Okay? If there is not a decimal, that's my not a decimal, we say that they are not. Okay? So, for example, for my not, if I've got the number 500, those 2 zeros right there are not significant. Okay? If I've got the number up here 50.0, then those are both significant. They don't have to be to the right of the decimal just has to be present, and they have to be following one of these guys here, one of these non-zeros. This is a great place for questions if you got them. Okay, last rule has to do with leading zeros. Those are the ones that are to the left of all of your non-zeros. What's the rule with them? They are not significant. So if I've got something like 0.0006000, and I've actually measured that out, then all of these leading up to that non-zero are not significant. The 6 would be significant because it's not a 0. All of these zeros here would be because they are following a not zero. So I'd have a total of 4 sig figs in that number. Okay, with me so far? Okay. There's a little more to it. Oh, last one, remember, is that if you have a counted number, those are infinitely significant. Okay? If I'm counting matchsticks, I'm not measuring matchsticks, I'm actually literally counting them, and I am infinitely confident that the number I counted is correct. Okay? I'm not relying on a measuring tool to do that, it's just a count. Because I want to talk about rules for rounding with sig figs when you're adding and subtracting, multiplying and dividing. When you're adding and subtracting, the idea is that you are going by place value of your least precise measured number. So let's say, for example, that I am taking 104.3 plus 19 plus 500. The first thing I'm going to do is I'm going to plug it all in my calculator. Even if I'm confident in doing it in my head, I know my head sometimes tells me lies. So I go 104.3 plus 19 plus 500. The answer my calculator spits out is 623.3. But now what I'm going to do is I'm going to look at my numbers and I'm going to find the one that is least precise with its sig figs. Which one would that be? It's going to be 500. Because there's not a decimal there, so what's the last sig fig I have here? This guy right here. What place is he in? He's in the hundreds place. So when I report this answer, how do I report it? That'd be 600. Okay. My answer cannot be more precise than what got me there. If I am doing multiplying and dividing, then what I do is I count sig figs, and my answer is going to have the smallest number of them. So if I have, say, 430 times 17.6, plug that in, so 430 times 17.6, I get 7568. Now I have to go back and count sig figs. How many sig figs does this first number have? It has 2, right? How about this one? It has 3. What's smaller, 2 or 3? So my answer can only have 2 sig figs. So I'm going to look at the first 2 digits I have, 7 and 5. I look ahead to see that the next one is higher than the 5 there. So that means I'm going to need to round. So I'm going to report this as 7,600. It still just has 2 sig figs, which is the same as this up here. A little bit confusing. We're going to get through this, and then we're not going to worry too much about this going forward. Okay? We'll worry about it again when we get to physics. Are there any questions about the math stuff? We spent the last couple of weeks talking about matter. We talked about the definition of matter. We looked at some properties and changes, and then we have spent this leading up to today talking about classifying matter. So first of all, definition of matter. There's 2 important properties that all matter has. Who can tell me what one of them is? Volume. Has volume. Okay? So all matter, we're looking to define it. It has volume, which means it takes up space. Okay? The other one's mass, right? And mass is just defined as how much stuff you're made of. Okay? And by stuff here, we're talking atoms, we're talking molecules, okay? But it's stuff. So if you are made of stuff and you take up space, then you are matter, okay? There you go. Argument's over. So we're talking properties versus changes, okay? A property is a characteristic. It's something that you can observe. It's something you can see, something you can hear, something you can smell, okay? Whereas a change is when something's actually happening. I'm just going to put it to happening. So if I walk by and I see that a dead squirrel is decomposing and there's maggots and stuff and it's all really nasty and stuff, would that be a property or a change? Change. Something's happening, okay? The squirrel is being broken down. It's being decomposed. A property of that squirrel might be the odor it's giving off, okay? Or the color of its little squirrely gizzard or whatever that's hanging out there. I don't know. Now, if we mentioned just a minute ago when we were looking at review the difference between intensive and extensive properties. Intensive, okay, it doesn't change based on quantity. Extensive does. I don't have room to write extensive, but it's just the opposite. Generally speaking, if you're trying to figure out if a change you're looking at is physical or chemical, the main thing you want to look at is does it result in or require interactions with different substances? If yes, then you're talking something chemical. If no, you're talking something physical. Okay? So, chemical versus physical. In a chemical change or a chemical property, you're looking at an interaction going on. You have one substance that is reacting to another substance. If I set a piece of paper on fire, that's only happening because the paper, what's in the paper, is reacting with the oxygen in the room and it's combining with it. If I take a chunk of sodium metal and drop it into water and it fizzes and explodes, it would not do that if the water was not there. Okay? So I can describe the change I'm seeing right there as a chemical change because it's reacting to something else and it's making new substances. And I can regard the fact that it will react as a chemical property. Okay? Typically, chemical properties changes, they involve lots of energy. They are usually harder to reverse. You end up with new properties or new substances. Physical, on the other hand, physical, you can observe physical properties without doing anything else to it, okay? So they can be observed alone. I don't know how I'd write that. I'm not going to worry about it then. Physical changes, we're talking little energy. Typically, a physical change is just a change in shape. Now, this doesn't just mean like folding it, breaking it, cutting it, squishing it. It doesn't just mean melting it or freezing it or evaporating it. All of those are physical changes, but it could also include dissolving it. Okay? If I dissolve salt in water, the water still has all of its properties and the salt still has all of its properties. The only thing that's changed about that salt is it has changed in shape. Okay? So, included in physical would be things like dissolving or undissolving, recrystallizing. It would include things like phase changes, so solid, liquid, gas. They are typically a lot easier to reverse. You don't get new substances. If ice melts and then boils, I have not made two new things. I've still just got water. Just part of it's water liquid, part of it's water gas. How are we doing on time? We're doing fantastic. Got about 3-4 minutes here. Last thing to talk about is classification into pure substances or mixtures. So if something is a pure substance, then it is going to have all the same parts. I'm going to say all the same pieces. Okay? In this case, the pieces are atoms, or the pieces are molecules. They're particles. They're all the same. If it's all the same kind of atom, then it's an element. If I can find it on the periodic table, okay, the PTE. If it's two or more kinds, or I can even go so far as to say one kind of molecule, it's compound. So then a mixture, going across here, are going to have two or more kinds of pieces. They are not all going to be the same. They're going to be put together in different ratios, different concentrations. If I can't tell that it's a mixture because it is so well mixed that it's actually all in a single phase of matter, then I say that it is a solution. Or a homogeneous mixture. Homo means same. Okay? All in one phase. If it's in two or more phases, if I can tell, hey, there's more than one thing in there, either by looking at it or by shining a light through it, then it's heterogeneous. Then it's either going to be a colloid or a suspension. Suspensions have big chunks. That typically, you can see them just by looking at them, or they settle out of solution. Colloids, the chunks are much tinier and they don't settle out, but they're still not all in the same phase. They are still chunks, just itty bitty chunks. And we are right at about out of time. Does anyone have any last minute questions that I can answer for?